Okay, so we might as well get started. Guessing this is everyone that's going to be here today. So clearly I'm not Dr. Atala. I'm replacing him for the week, but obviously I don't know if you guys ask questions normally during the class or if you wait till afterwards. I don't mind either way. If you're confused during the lecture, I'd rather you just ask me right away. We can clear it up. Chances are if you're confused, someone to your right or left is also confused. So feel free to ask me whatever question that pops into your brain. So today, we're going to be talking a little bit about numerical weather prediction and sort of what we use it for, why we use it, sort of that type of thing. So to begin, what do we use numerical weather prediction for? So generally, we use it for, its main purpose is for weather forecasting, right? So when you go on Meteo Media and you see what the weather is going to be like in a few days, we're using numerical weather prediction models to actually sort of make that happen. So sort of what we have here, here's a good example, is the superstorm that happened in 1993. Sort of this was a huge storm that affected sort of the whole east coast of the United States and Canada. It dropped sort of a whole bunch of snow and rain all across, up to 120 centimeters in some areas. And this storm was particularly sort of intense in that it was the lowest low that we've seen sort of ever, minus that of sort of like a hurricane center. So that obviously has a stronger low than what this has. So here's just an example of what we would use a numerical weather model for, sort of in weather forecasting means. So other than sort of forecasting weather in the future as like a predictive state, what we also use models for is to actually sort of get more information about things that we can't really see or get data on, right? So a thunderstorm, for example, we can't really get much data as to what's happening in the center of it, right? Like you can't fly a plane through it. Sort of whenever you're flying and you see a thunderstorm, they always go around. You don't want to go through it. We could try and use instruments like radars or balloons or what have you, but those aren't going to give you the whole idea of what's happening in the thunderstorm. And chances are if you throw a balloon up in the center of a storm, hail's going to hit it, lightning's going to hit it, and you're not really going to get much information anyways. So what we do is we sort of know generally how the dynamics of how a thunderstorm works. So we sort of make a model and sort of run it and see what comes out of it. And that's going to give us more information about something that we can't really get information on. So granted, it's possible that what we're getting isn't actually realistic. But if it sort of looks like a thunderstorm and acts like a thunderstorm, we're going to take it to be that it's actually a thunderstorm. And from there, we can then sort of get more information about what's going on in the inside. So that's sort of two things that we use models for. So weather forecasting, and then to sort of get a bit more information about things that we can't actually get data from. Okay, so how exactly does, in terms of weather forecasting, how exactly does it work, right? So there's three kind of major steps when we're talking about weather forecasting. So I don't need you to memorize this whole thing. There's a lot going on here. Really, there's sort of the three parts that I want you to focus in on, and that's what we're going to talk about a little bit today. So at the bottom here, sort of this area, just draw an arrow, we have sort of data collection. So the first step is to initialize our model. We need to get a whole bunch of different types of data to put it into the model to say this is what we're starting with. So the starting point is this. So this is a whole area of research in atmospheric science. People take data from radars, they take data from satellites, they take surface observations, they take balloon soundings, and they somehow need to manipulate it in different ways so that we can throw it into a model so that the model understands it, right? So that seems like it could, be an easy job, but it's actually really, really difficult. So you need to do sort of quality control on it to make sure what we're getting, say from a radar or from a satellite image, makes sense, right? So sometimes instruments give us back things that don't make any sense. We need to do quality control, make sure it's okay, before actually now starting, like initializing our model with it, right? So that's sort of the first step. Grab all the data, sort of organize it, and then now throw it into our model. So the second step is the actual model part, right? So that's this sort of big sort of area here. And now this is a whole nother area of research inside of atmospheric science. So what we have here is we have all the equations, all the dynamics, all the physics. So everything that you can think of that's happening in the atmosphere, sort of clouds, radiation, all of that stuff is happening in this section. So some things, like sort of how winds move, we have equations for, right? We actually have an equation that you or me could just sit down and solve. We can figure that out. So that's some things that go into the model. Those are equations that we can figure out. But there's other things that we don't actually sort of know exactly an equation for. So those are other things that we somehow need to represent in a model somehow, right? So how a cloud forms, for example, we don't fully know how it works. Like, we have a general idea, but we don't have an exact equation that says, if you have this, you're going to get this type of cloud, right? But we still need to somehow represent it inside of the model. So this is where sort of we have different techniques of doing that, but it still needs to be represented, right? So inside of our model, we have all these different things. We have the equations, we have the physics, we have all different types. And so we throw the data into these equations. The equations does its thing, and then it pops out an answer, right? So this answer that it pops out, right, so that's going to be like this top step sort of up here. The answer that it pops out, we don't just give to you guys, right? Like, if you look at, an Environment Canada weather like website or Meteo Media or whatever you guys look at for weather, the answer that just first pops out isn't what you guys see, right? So it takes a sort of human intervention to look at it, to make sure it makes sense, and do some post-processing on it, right? So we take a look at it. Do the numbers make sense? If you look outside and our model gave that it's raining but it's clearly sunny, we're not going to put that as our forecast, right? That doesn't make any sense. So there's multiple ways that sort of people deal with this. What we tend to do is we get an answer, we see if it sort of makes sense, but then what we do is we restart the model, changing our data, our initial conditions here at the bottom, the first step. We change them slightly, and then restart the model again. If we get an answer that looks similar to our first answer, it's sort of, we have confidence, right? Like, that makes sense. If we're getting something that's close and we sort of tweak the initial conditions a little bit, it makes sense that forecast seems to be slightly accurate. But we don't just do this once or twice. We tend to do this like 50 or 100 times. So we do it a lot of times to see sort of the answers that we're getting are actually close to each other. And if we get 100 or so answers that are close to each other, we have a little bit of confidence in the forecast that we're going to give, right? So we get a whole bunch of answers, and then what we do from there, we play around with it, and then that's sort of the forecast that you guys would see. Like, if you looked on a website, or whatever website you look at, that's been played around with and then given to you guys, right? But different organizations play around with it differently. Like for Environment Canada, in Canada, they only use a human intervention for the first 2 days of the forecast. So if you go on the Environment Canada website, after 2 days, basically that's just what the computer model is giving, right? No human has looked at that, has played around with it, and has dealt with it. But in the States, sort of some of their models, they do it for the whole 15-day forecast. So a human has gone in for every single day, looked at it, played around with it, and said, okay, this makes sense. This makes sense, we think. Right? So it depends on where you're looking or what you're doing. Every sort of organization or country has different ways of doing it. Right? So that's sort of important to keep in mind. So really the important thing here is that there's sort of three processes, right? We have the initialization of the data, so we've got to play around with the data, make sure the initial stuff makes sense, throw it into the model does its thing, and then it pops it out, and we have the post-processing, right? So there's sort of 3 steps to getting a forecast out there. Is that okay? Everyone sort of understands that? It's maybe not that complicated. Okay, so what exactly is a numerical weather model, right? Like, what do I mean by we initialize the data? So here's just sort of like an example of what we mean. So this is sort of, you got North America here, right? Somewhere around here, and then you got sort of like all the other parts over there. Each black sort of dot or sort of cross is a point that we need to put data into our model, right? So each of those dots represents where we need to put some type of information in there. So over land, this isn't too hard, right? We have a whole bunch of different types of techniques. We've got, like, they send up balloons to get like a vertical profile of the atmosphere. We have radars that are there. We have some satellites that can do some things. So over land, it's not that bad. We have a lot of available data for us to put into the model. Where problems start occurring is where we don't have data, right? So like over the ocean, we clearly don't put up balloons over the ocean, right? That seems pretty impossible. We do this, sort of the balloon scare, the data comes in twice a day at like 00 UTC and at 12 UTC. So clearly we can't put in balloons everywhere that there's dots sort of over here in the ocean. So we have a few techniques to sort of deal with this. They're not great, but we have to do something. So the first thing we can kind of do is there's always satellites sort of flying around. So we can use the information that satellites give us, right? But that doesn't always give us all the information that we need. And some points, say like a random point like down here, right? If a satellite misses that for some reason, we still need to put in information in there. A model doesn't accept not having a point. So what we do, which isn't great, is we initialize the next forecast with the end of the previous forecast. So say we're forecasting 12 hours from now, and I'm initializing now, and for some reason at that point right there, there's no data. I'm going to use the information that came from the last 12 hours. So the forecast that ended right now from 12 hours ago, we're going to take that information and initialize it for the next 12 hours. So clearly that's not great, because if there was a problem, in the first 12 hours, we're now just pushing that problem forward, right? But we don't have any other technique right now to deal with these types of points, right? This is all that we can sort of come up with right now to make the model actually just function and work. So in addition to this, right, resolution is also an issue, right? By resolution, I mean like how far, so here there's just like a lot of black dots, how far each of those black dots from each other, right? So back in the days, like 20, 30 years ago, our resolution wasn't great, right? Computers weren't as sort of strong as they are now, and we would have resolutions on the order of like 100 kilometers. So each point are 100 kilometers away from each other. So where we put in the data, that's how far they are, right? But clearly there's some like mountains and lakes and stuff that are more than 100 kilometers away from each other, right? Like they're closer than that. So the resolution of your model really matters, right? So on the left here, we have a resolution of 22 kilometers, right? So that means that each point from each other are 22 kilometers away. And on the right here, we have 12 kilometers resolution, right? So clearly 12 is, has a better resolution than 22. And when we're looking at mountains specifically, the 22-kilometer one has trouble resolving the peaks of the mountains just because it's not fine enough. The resolution isn't good enough to see that there actually is, a mountain happening there. Whereas on the right-hand side, now that we're getting sort of smaller, right, so the points are closer to each other, now we can actually see that there's a peak, right? There's a mountain peak there. And when we're talking about forecasting, mountains are a big deal, right? If we're missing the fact that there's a giant mountain somewhere, when you're forecasting something, the weather is going to completely change, right? We're going to have different winds, we're going to have different temperatures. There's all different other effects that are going to happen by just, having a mountain in a location. The model seeing that there's a mountain, right? So the distance between points is really important. And in this day and age, right, our computers have gotten a lot better. So this isn't so much of an issue, but sort of back in the day it really was, when the points were really further apart. So here's just another, like a good example, I think. So on the bottom here, we have like a low resolution model, and on the top one here, we have high resolution. Right, so high resolution meaning that the points are closer together, and low meaning that they're further apart. And here we have sort of Montreal and this little star here. So in the lower part here, right, so Montreal's surrounded by a whole bunch of different mountains, right? We've got the Green Mountains, the Adirondacks, the Laurentians. It's surrounded. We're in a valley, right? So in the lower one, the model doesn't even see that there's a valley, right? It doesn't really see it. And on the top, here we can clearly see that it's inside of a valley. So the fact that the model can't see that Montreal is inside of a valley can really change the weather that it forecasts. Specifically, today is a great example. We've had sort of like freezing rain, ice pellets, and snow all across the board, right, today so far. And that's mainly due to the fact that we're in a valley and we're channeling winds down there. Now, if the model doesn't see that we're in a valley, it's not going to forecast all this sort of the precipitation that we've had today, right? So resolution is really an important part of getting things right in a model. You're just giving the model a better chance if you have a better resolution, right? So that's just a good example, I think, for today specifically. Okay, so the map I showed before was an XY plane, right? So that was just showing sort of North America as like a flat plane. But clearly, the atmosphere is 3D. We live in 3 dimensions. There's a vertical direction as well, right? So the model has points in the XY direction that are evenly spaced. But then in the vertical, we also have different levels, right? And this is sort of a general distribution of how pretty much all numerical weather models work. What we do is we sort of think this might work. Okay, so we're going to get back to this. So what I was saying, right, is before I showed you a map that was XY, right, it was sort of North America with a bunch of other parts. But clearly we're in a 3D world. We've got, sort of 3 dimensions happening. So we need a vertical direction as well. So here we have just a general distribution of what the layers, sort of the locations of where we need to have data points in the vertical are. So as you can sort of see, we have a concentration sort of more around the surface. And then as you move further up in the atmosphere, sort of the resolution starts to decrease. So the spaces between to the lines starts to increase a little bit more. So the reason we do this is because we live near the surface, right? We care more about what's happening at the surface than what's happening, at 25 hectopascals, which is, way up out there. So we sort of concentrate the information that we want to know right at the surface. So we have sort of an increased amount of resolution here, and then sort of it decreases as we go vertically upwards. So here's just an example of like what we would get from a forecast model here. So in the black, we have, this is the sea level pressure sort of at the surface sea level pressure. And then sort of your dotted lines here kind of represent, they're sort of, you can think of them as temperature, sort of. Where the blue represents the 50% chance of getting snow, and the red represents sort of your 50% chance of getting rain. Right? So right along this border here, we have a 50% chance of rain and a 50% chance of snow. Whereas when we move more sort of into the blues, we have a higher probability of getting snow. Move more into the reds, we have a higher probability of getting rain. Right? So when we put all the information into our models, this is the type of thing that you'll see that comes out. So you can see sort of like low pressure systems, high pressure systems. Like this is the type of thing that you would, if you were a forecaster, you would get used to seeing. This is just sort of an example. Okay, so there's sort of across the world maybe 6 or 7 models that are used, and of those 6 or 7, about 3 to 4 of them are sort of generally counted as being better than the other ones. So here's just a general table of the information of those different models. Some of these should probably be updated. I think the resolution's probably gotten better, over the last year. But the three best sort of models that we have across the world are the second one here, this Global Forecasting System, the GFS. Where is it? This one down here, the European Center for Medium Range Forecasting, and the last one here, which is the Global Environment Mesoscale one, which is what Environment Canada uses. So of those 3, so those are kind of the top 3, the best one by far, sort of above and beyond, is the European Center for Medium Range Forecasting. And then after that, sort of in a distant second, is sort of your Global Forecasting System, and then sort of close behind that is the one that Canada uses, the Global Environmental Mesoscale Model. So when we say that one model is just way better than the rest, that doesn't necessarily mean that every single forecast that the European Center for Medium Range Forecasting gives is going to be better than all the other ones. It just means that in general, sort of out of, say, 1,000 forecasts, that one's going to be better than the other ones. Right, but on any specific forecast, one might do better than another one, just depending on how they play around with the information that they give out. So that's just a general sort of idea of sort of how our forecasts are sort of today. Okay, so I sort of briefly touched upon this, but we clearly have limitations to weather prediction models, right? If we didn't have limitations, then weather forecasting would be perfect, and you would know what the weather is from now until sort of forever, but we don't, right? As you probably know, give a few days, that's sort of the max to what we can sort of do well at weather forecasting. So why do we have problems forecasting weather? So there's sort of 3 general reasons. Our first is that we don't have exact equations. So for things that, like the wind, we do have an exact equation for, we can solve it. But there's some things that we just don't know exactly how they work, right? So we have to make parameterizations for those processes to make the model actually function and work. Another one is our errors in the initial conditions. So that data that I was talking about that we input into the model, we're going to have errors with that. And I'll talk about that a little bit later. And sort of our inadequate resolution isn't such a big deal anymore. Sort of in this day and age, we've sort of got the computer power that we can get to a resolution that works pretty well. In fact, the resolution that we use now is actually better than the resolution of the data that we're inputting into the model. So that's sort of not as big an issue. It's really the first two that are what sort of makes the forecasting not as great as it could be. So, okay, when I'm talking about parameterizations, there's sort of two different ideas here that we're talking about. So one problem is that computers, because of the resolution, computers might not be able to resolve or sort of, if you want to see everything that's happening, right? So things are happening on such small scales that the computer model can't actually see what's happening. So we just kind of have to, between grid points, sort of make a good guess at what's going on, right? So because it can't see everything because of the resolution, we have to just sort of smooth things out a little bit. And then another thing, which is probably the bigger problem, is that we don't know exactly what's going on, right? So specifically, let's just sort of take the idea of like a cloud, right? So we know kind of how a cloud forms, right? We know sort of the general processes, but we don't know the exact specifics, right? So we don't know how many aerosol particles there are in the atmosphere at the time that a cloud forms. We don't know the size of them. We don't know sort of, once a cloud forms and it starts raining, right, you've got evaporation or cooling. We don't know exactly how much cooling is happening. These are all things that we're making best guesses at. So what people have done is they've done field experiments, right? So they go out into the field, they take a look at what's going on, they take down data points, and then we make like an empirical relationship, right? So we say, when this happened, we saw this happen. So we make kind of like an equation in that way. So it's not perfect, right? It's not always going to follow that exact relationship, but that's the best that we can do right now. So those are the things that are going into the model, these sort of empirical relationships that say, if this type of cloud is formed, we expect this type of cooling or this type of heating to happen, right? So it's not perfect, and that's one problem that we have inside of our models. So in addition to that, there's also, problems with like radiation, right? So we've got particles in the atmosphere that scatter light. How much are they scattering? How much are they scattering back into the atmosphere? How much is going back to the Earth? These are things that we're not 100% sure about. We're getting better, we're understanding a lot more, but we're still not 100% sure this is going to cause this to happen. So inside of our models, we have that problem going on. But, okay, so here's just an example of, say, if we sort of put a cloud into a model, like what would kind of happen, right? So all the X's here are the actual grid points in the model. So these are the points that the model sees. And we have sort of the white here is our cloud that's being formed, and the blue is the evaporational cooling that would happen once sort of we get some rain going on. So as you sort of see it evolve, you can kind of notice that the cloud's happening between grid points, right? So you sort of see it spreading out, and it's only at sort of one grid point that the actual model sees what's going on. So if we didn't have these parameterizations, the model would only see the cloud at this one point over here at the end of the simulation. But that's clearly not what's going on, right? There's clearly a cloud going on in this sort of area, but a model can't specifically see that. So that's where sort of the different parameterizations come into play a little bit, to make sure that we do know that there's a cloud, and that once it does hit a grid point, it knows that it's there, right? So that's sort of important when we're talking about weather forecasting, sort of. But sort of the biggest problem, I guess, is our sensitivity to initial conditions. So basically what we're talking about here is chaos, right? Not chaos in the terms of everything you have is disorganized, but more chaos in terms of the fact that if you put in sort of initial conditions, right, sort of into our model, if you change those initial conditions slightly, I mean slightly by like a decimal point, that's going to cause your forecast to be completely different. So that's what we mean by chaos. So like I think a good example of that, I don't know if you guys have seen it, but there's like a Simpsons episode where Homer goes back in time and like steps on a fly, comes back, and like is in a totally different world. Like that's chaos, right? So we changed something tiny, and when he moved forward, the whole world was completely different. So that's sort of what's going on sort of here. So if we just, I'll try and not make this too complicated, but sort of basically what this is you can think of it as like a probability distribution function, right? And you can think of each of these two different circles here as two different forecasts, right? So say this top one is, your warm and dry condition, and then this bottom one down here is, say, like wet and cold, right? So they're two very different forecasts, and what we have here, the different lines basically just represent where the forecast is going to end up, right? So say we have, say we're lying sort of on, I don't know, like this line, right? So our initial conditions say that we're on this line, right? And so that's going to spiral into the wet and cold forecast. But if we change those initial conditions slightly, right, where we're just sort of over here, which isn't a huge change in our conditions, we're now going to end up in the other forecast. So we've changed these conditions very, very slightly, but we're getting two completely different answers, right? So the sensitivity to the information that we put into the model is really high for some cases, right? So for other cases, like let's say, we put our initial data starts like here or whatever, even if we change it a lot, like even if we put in this stuff, you're still going to end up in that same circle, right? So it's not always true that the initial data that we put in is going to be sensitive and it's going to diverge into completely different answers, right? It's just in some cases, the initial conditions are very, very sensitive. And so this is the inherent problem of of weather forecasting, this problem right here. So here we have this, I guess this goes back a little bit to before. So all these dots are basically locations where we can get surface data. So this is across the world. So obviously some areas there's more and some areas there's less, right? So this is just a general understanding of the sparsity, especially like over water, of where we're getting the data to put it into the model. Yeah, I think we sort of talked a little bit about that. Okay, so one way that we can sort of mitigate the problems of, just our initialization problem is, so we start a model off with the data that we get. We throw it into the model, it pops out an answer, right? If we take that as the truth, then we could be horribly wrong, just like I showed before. If our initial conditions are slightly off, from our data not being perfect or for whatever reasons, then you're just going to get a completely wrong forecast. So what we do is we can restart this model by slightly changing the data, like changing decimal points of the initial data, and rerun the model. And then another answer will pop out. And we can keep doing this a whole lot of times, 50, 100, whatever amount of times that you want to actually do it. And what we end up getting is something called an ensemble prediction. So this basically is just going to give you the range of possible answers if we just sort of like fudge around with our data a little bit, right? So here's sort of a good example. So at the starting point, right, all the initial conditions are pretty much the same. We're only changing it slightly. We're not changing it drastically. But sort of so these numbers are just the days of the forecast. So but as the days go on, sort of all you can see is these blue lines, which are all the different forecasts, start to sort of spread away from the mean here that we have in our black line, right? So all the answers still end up generally in the same area, right? They sort of start in this area and end up sort of like in the Sea of Alaska over here. But there's drastic differences between sort of, if you go like a forecast down here or a forecast all the way up there, we've got big differences, right? So this is one technique that we can use to try and deal with the fact that we know that our initial conditions, if they're slightly off, are going to cause horribly wrong answers. So we just run it a whole bunch of times, and then we can take the mean of all these different forecasts and say, okay, so this is a general idea of what we think is going to happen. All the answers gave us this general sort of look, and we're now just going to take the mean of them, and this is what we're going to give as our forecast. So when we're for ensemble predictions, it's not necessarily just for the initial conditions, right? As I said before, some of the parameterizations that we do for clouds, radiation, whatever, we don't know the exact equations, so we can sort of play around with those a little bit too. So if we sort of have an empirical relationship where there's sort of a constant value in there somewhere, we can play around with that constant, and then that's also going to give us a different forecast, right? So we can play around not only with the initial conditions, we can play around with the actual sort of parameterizations that are inside of our model. So the combination of playing around with both of those gives us a whole bunch of different answers. These whole bunch of different answers can sort of give us a better idea of what's actually going on and give us a bit more confidence as to what we're seeing. Okay, so here's an example of what I mean by ensemble forecasting. So here on the left, here let's go over, I guess, all the lines here. So our green here is like our climatological value. So it's the mean value that you'd expect to see, from like looking sort of in the past. All these different, the white here is the mean, and the light blue and sort of the dark red here, are all our ensemble runs. So those are all the different times that we restarted the model and got different sort of answers for it. So to start off, so day 2 of a forecast, right, we'd expect things to be somewhat similar looking, right, not much, there shouldn't be a reason why it diverges so quickly unless we've really put in bad initial conditions. So here we've got sort of everything lying on top of each other, looks pretty reasonable. But now when we start talking about day 15, which when you look at a forecast, they do go out to day 15. Now we've got things going all over the place, right? So we've still got our climatological mean here. That's not going to change. Our white here is our mean still. But these blue lines are kind of going all over the place, right? So after sort of a certain number of days, you know, it diverges so much that any one forecast can be completely different, right? So one forecast can say that it's going to be, you know, 15 and sunny. Then if you take one of the other ensemble runs, it can say that it's like -5 and freezing rain, right? So it really, after a given amount of time, you can see that these runs just completely diverge, and it sort of becomes hard to understand what's going on, right? So that's sort of the whole chaos idea, that just changing it a little bit really alters sort of the patterns that we see. Okay, so this was just to take a look at what's happening kind of today. Well, I guess this was actually from yesterday, but then it'll be the forecast for like the next few days, just to take a look at sort of how these spaghetti plots sort of look in a real example. Like that example before was from a while ago. So this was taken from yesterday, and this is sort of the same thing. We've got our white here is our mean. The blues are the different ensemble runs, and same with the reds. And so this was last night, and this was sort of the day 1 of the forecast, right? So still everything looks pretty good. Everything's sort of, you know, lying on top of each other. The forecasts all kind of agree with each other. So we can have pretty high confidence that this is what's happening. If all the runs sort of look the same, that sounds like it's a pretty good idea of what's going on. And if we sort of just step through sort of the days as the forecast moves on, we can sort of take a look at what's happening with our runs. So now this would be day 2, so that would be like today. You can even start to see that the blue lines are starting to separate a little bit. So even after 2 days, right, that we can start to see that each of the different runs aren't all aligning with each other. So it's not always going to be that, you know, after 5 days they completely diverge. So some conditions, if they're relatively stable, some conditions are always, you can have a lot more predictability. So we could have up to say like 8-9 days where all the runs are sort of on top of each other. Then there's going to be other times where the conditions are really, really sensitive to what we're putting in, and that's when you start to see them diverge sooner. Right? So it really depends on the circumstance of the atmosphere at a certain time and sort of how sensitive it is to the change in our initial conditions. So this just shows sort of like day 2. I think I've got a few more. Right, so then start now day 3, we can sort of start to see them sort of be a bit more wiggly, right, a bit more spaghetti-like or whatever. And then day 4, sort of same thing, they start to diverge a lot more. Day 5. And right, so you're getting the point, right? So the further we move on, the more that they sort of start to have a bigger spread. And at this point, we start to lose a little bit of confidence in what the forecast is, right? At this point, we don't really know exactly what's going on, but it still is giving us an idea, a general idea of what's happening. And then this is day like 8. Stuff's going all over the place, right? We've got squiggles kind of happening everywhere. So what we're supposed to get out of this, I'm not too sure. You kind of have a general mean, but there's sort of lines happening in all directions. So at some point, the forecast is just a general guideline and shouldn't be taken too seriously. But yeah, so that's the general idea of spaghetti plots. Is that okay? Does everyone understand that? The importance of, yeah, go ahead. Sorry, the green line is the climatological like mean. So that's the value that it generally has at this time of the year that we've calculated, say, from the past 30-ish years. Is the actual mean, right? So if you add up all the different sort of ensemble forecasts and take the average of it, that's where the white's going to be. Yeah. Okay, didn't really want to start into that. Okay, so anyone have any questions? That was sort of, that's okay. Right, so the biggest important things is like basically our initial conditions, parameterizations, all that stuff. I didn't really want to start on balances today, so it's really early though. could just stop for today. If you guys have questions, you can come ask me. Does that sound okay? Yeah? Go outside and enjoy the weather? Yeah. Of course. Yeah, sure. No, go ahead. I can turn lights on, can't I? Or if you have any assignment questions, feel free to come ask me as well. There's got to be lights somewhere. Room light on. Lighting control. Well, those turned on. On. Just go for it. Yeah.
So there's this question, it's going to come up. The question number 7, I was just wondering, can you use the same, because in our notes we have this chart that gives us the saturation vapor pressure as a function of temperature.
Yeah, 100%.
Do we have to use, like, I'm just going to take out the question, I'm sorry.
Can you use the vapor pressure for the temperature? Is that what you're...
dew point temperature.
Of course.
Okay, so
They're
it's the same chart.
They're the same thing.
Okay.
Literally, that graph is just to show you temperature versus the amount of vapor pressure that it can hold at that temperature.
Okay.
So whether we're talking about dew point or actual temperature,
It's the same. Okay.
it's a temperature versus vapor pressure graph.
Okay, and
Yeah?
when they ask us to find the dew point temperature and they give us the vapor pressure, we don't really need the ambient temperature for it. We just go on the chart and see like
Whatever it
the
is.
vapor pressure. Okay, it's good.
Yeah?
And thank you. And
Yeah, no problem.
there's this question where they ask us about relative humidity that we have to compute it, but then it's really when you write the answer, let's say it's 26%.
Yeah.
When you write the percentage sign,
It doesn't like it.
Exactly. So do we?
I would just take it out. Just write 26.
Okay, not 0.26.
We know that you're... Yeah, no, I would go with 26.
26.
Yeah,
Really?
we know that you're talking about percent.
Okay, and
Because relative humidity is times 100, right? Like,
Yeah.
that's the formula.
Okay, so do we put like decimals or like rewrite
We
it
give
to-
a range.
Okay.
Like anything that is, I think, between, so say the answer is 26.
Yeah.
Anything that's like 25 to 27 or 24 to 28, we're okay with.
Okay, so
Yeah.
okay, because the actual answer is like 26.07, so we can
If you
just
put
write.
whatever,
Okay.
we're going to accept a range. Because we know that people, especially grabbing numbers off like graphs,
Yeah.
people are going to grab it.
Okay, thank you.
As long as you have the general idea.
Okay.
Yeah?
And oh yeah, this is my last question. When
Yeah, no
they
worries.
ask us about like in which regions the pressure is going to be higher or lower, like they give us actual cities or like places around the world. Do we take like the actual altitude of the place or like its level compared to sea level? Because I know the higher we are, the less particles we have above us, so
Right,
basically
right.
lower the pressure.
Right?
So do we? I don't know if it's like compared to sea level or the actual altitude. Like
Okay.
if we compute like a little like altitude of I don't know the Empire State Building.
So
or,
what is the question exactly asking, just to be clear?
The question, the one about like we have to put the orders of the different places.
Oh, Calgary, Alberta.
Yeah, exactly. Yeah, I just wanted to know if it was where is the I think it was question like number 2.
Sinon, j'ai l'écran de filiation.
Okay, but she's
Ok, c'est bon, c'est bon.
question number this one. So it's pretending to get barometer
As a present. Who would give a barometer as a present? Sorry, continue.
And then it says sort these starting with the location that you would expect have the highest pressure to the lowest. So is it basically like you find the altitudes of each
Yeah,
of
like
them?
exactly.
Okay.
So you kind of want to, like, if you're on top of the Rockies versus
Yeah.
if you're in Montreal, right?
Okay.
Yeah? Does that make sense?
So the higher are the lower the pressure
Exactly.
is.
Yeah.
Okay. And when they ask us for the pressure outside of the plane,
Yeah.
do we still consider like okay we're just outside of the plane at the same level, so the number of particles that are above us?
I believe so. They're saying it's flying at a constant altitude.
Exactly.
Is that question?
Yeah.
Yes.
Like from Montreal to like the Dominican Republic.
yeah.
Yeah. So basically, since it's harder in Dominican Republic,
Yeah.
The molecules are like more expanded, and we have more molecules above the plane. So I would assume
Il y en a plus,
there's more low.
Okay, so let's think about this, right? This is sort of a weird one.
sur le pourcentage, là.
Ah ouais. Pour le pourcentage, je vais tout faire sur le pourcentage.
Okay, let's just try.
26?
Genre, ouais,
T'étais
pas
pas au point
0.26?
26?
Non.
Ok. Mais je pense que...
Okay, so you're saying that you're flying Montreal. Everyone? Yeah? Okay. Yeah, this one's sort of weird. So you're flying here, and you're flying in this direction, right? And you're actually Didn't you guys chat about jet streams in the last one? Or am I? Yeah, it was, I think you may have chatted about it a little bit, but I can go over it. I'm more than okay with that.
Sure. I just don't have anything in my notes about jet streams specifically. Just as asking about whether it'd be stronger in the summer or the winter, and like that's what's listed, but not in my own notes. I just have like well somewhere. So
Okay, so basically like a jet stream is the super duper fast winds that we have at the top of our atmosphere, top, like 500-ish bars. Like it's the really really fast winds. I think he showed like a map of it last class maybe.
Yeah, it was like a couple classes ago.
Or was it a couple? I think I looked at it. We can just take a look at it. Let me see what we've got here. Right, I think I saw it. Let's just do a PDF. It's easier. Right, I think I saw it at the end here. Yeah? Does that map look familiar?
yes.
Okay, so here, this is basically what he's talking about. Like this really fast wind, like here we're really high up in the atmosphere. These are sort of, this is the jet stream. It's like the really, really fast winds that we get up there, right? Okay, has he gone over where, like why we get these winds? Has he talked about that at all?
Not that I can recall. I don't know.
Cold winds coming from the north, like heat, warmer winds coming from the north, there's like an overlapping in between. That's why we get winds going from one direction.
Okay, so basically he's talked about that your temperature difference is what causes winds, right? He's talked about that a little bit.
I thought
Like
it was pressure, like moving from a area of like different pressures.
Okay, so pressures and temperatures in the upper atmosphere are very, very related, right? Like as we showed there, higher pressure in the upper atmosphere means higher temperature, right? Not at the surface. The surface, don't think about that at the surface, but higher up, if I have a high temperature, I'm gonna have a higher pressure. Does that sound familiar? Okay, so those two are sort of interrelated, pressure and temperature. So if I say that a temperature contrast is causing winds, I'm saying the same thing as a pressure contrast is causing winds. Does that make sense? Okay. So if a temperature difference is what's causing, or pressure difference is what's causing these super duper strong winds, in the summer and the winter, do we have a bigger contrast between the equator and the North Pole?
I think so, yeah.
In the winter, right?
Yeah.
That's, in the summer it's not as bad, the equator sort of stays the same, but in the summer we get really, really warm-ish. So that's why in the winter we tend to have way stronger winds, because there's such a bigger temperature contrast.
Because it gets very cold in the
How much of
but
a
it stays sort of the same.
Exactly. Sorry, yes.
How much of a description is he expecting for that question?
I mean, not that much. Like, you could probably say it in like 3 sentences.
Yeah, there's like
Right?
a 5,000 word cap, but like I
If
essentially
you go to that 5,000 word cap, I'm just not going to read them.
it's just yeah, it's I don't
Character, okay.
understand how you
Like,
could possibly write that.
no, that's it. So that, I think he just gave you a lot more than you need to.
Change the sensor, like bigger difference in pressure levels causes for the streams to be higher.
Sure, sure.
Or
You should be able to, like, if you, the, I would say try and keep it as short. Like, the more that you write, chances are you're going to write something wrong. So if you try and keep it shorter, but you know what you're saying, then it's probably better. Yeah?
so yeah, so he talked about like winds in terms of pressure, but if we were in this question to say there's a bigger difference in temperature which causes
So
stronger
if-
winds or
Because
something.
the temperature, the difference of a bigger difference in temperature causes like a big difference in pressure.
So only in the upper atmosphere. If you're going to say the temperature and pressure are like interrelated, you need to say specifically the upper atmosphere. Because that's not true at the surface, right? If that was true at the surface, when we're cold, we would always have a different pressure than the equator. But that's not true, right? We generally get about 1,000-ish on any given day. So if you're going to say temperature and pressure and relate them, you need to write like we're talking only about the upper atmosphere. Does that make sense?
You have to mention pressure and temperature. Because I only mentioned temperature.
You don't have to, but if you, same thing, if you just say that the temperature contrast is the biggest, I would maybe throw in that we're just talking about the upper atmosphere. I would say that we're maybe only talking about the upper atmosphere, right? Because the jet winds the winds that we're talking about, they're not at the surface, right? Like they're higher up, and that's sort of the area that we're talking about. Maybe just throw in the word upper atmosphere, just to make sure that it's exactly safe and not sorry. Yeah? Does that make a bit of sense?
And then I just had a question about number 8.
Mm-hmm.
For this map, I was just confused about, because I remember in the lecture he was talking about like how you would read these maps, and I know like he focused a lot on how like around low pressure systems winds move counterclockwise, and like you would generally expect warm weather to the east, I
Yeah.
think, and cold weather to the west. Wait.
Yeah, you're right.
Yeah.
So why?
Because in the
okay,
so
so
it's bringing.
we're totally talking about wind direction, right?
Yeah.
Perfect.
So then, when you're reading this map, I was just confused about, um, like how exactly you're supposed to infer the temperatures because, like, here, so the wind moves in the direction of the ice bars. So here it's moving clockwise, or wait, here it's moving counterclockwise,
Forget
and then
about clockwise or counterclockwise. Which direction are the winds?
they're going from west
They're,
to east.
not at, like, so west east
From-
would be this, right?
Yeah, so they're coming from like the northwest and then moving.
So moving downwards. So what air do you think these winds would be bringing?
These are bringing cold air, and then this would be bringing warmer air up. Okay, so that's
Yeah?
so it's not really you don't really have to think about like where the low pressure system or the high
Not fully, not if he gives you like a map like this. But what you said is 100% right. Like if he gives you a low and doesn't say which direction the winds are going, like if he doesn't give you the arrows, then he's expecting you to know that the winds go this direction, which means we're going to bring warmer, blah, blah, blah,
Right.
blah, blah. But in this case, it's literally just like which direction are the winds
Okay.
coming from, where, air masses are they bringing, or most likely to be bringing.
Just to be sure.
And I'm assuming it doesn't matter where in the circle you put
I
it,
no,
just
I don't think so.
anywhere.
Yeah.
Okay.
Just to be sure this is like a low system. This is a hot system.
Yeah, so like your low would be somewhere sort of like here, and then your high would be somewhere sort of like here, ish.
And like how do you know that based on how did you know that?
Can we just say magic for now?
Yeah.
Like, it's just, so no, there's other things that go on, but basically like so this is a trough, right? He talked about that. You've got a big old trough here.
Is this like the cold air dome thing?
Yeah, sort of. Okay.
Okay.
But if that's something, like if you actually are interested in that type of stuff, like that's sort of what the classes like higher up in atmospheric science talk
Right.
about. Or
But,
just like,
for the
yeah,
basis
love
of-
weather.
For the purpose of this question, it's like not.
No,
you
so
don't
like,
need to
yeah,
know.
this
Okay.
purpose is really just where are the winds coming from, what type of air mass are they bringing, is it cold, is it warm?
Okay. Thank
Yeah?
you. Yeah. Thanks.
No problem. Is that okay? You guys are good?
Yeah. I just have a quick question for the barometer.
Sure.
Is it like Mount Everest the highest pressure? No, it's lowest probably.
Yeah, I think you've gone the wrong way. Yeah, because you're high up, right? So the higher you go, pressure decreases.
Based from the sea level.
Yeah. Right. So if you like hike up a mountain, it's like you can't really breathe as well and all that because your sort of air is getting Cool. Yes. I don't. Whoever.
I just had like a really quick question. Is
Sure.
today's lecture going to be like was it recorded?
It should be if I did everything right.
Oh, okay.
I hope I did. If not, good you were here.
For the same barometer question.
Yeah.
If you're comparing the temperature or the pressure between New York and Calgary, how do you sort of compare the pressures? I mean, are you going to look at the temperature to make like a comparison
So
between which one has the higher pressure? Or
So the temperature-pressure relationship doesn't work at the surface.
Right.
The temperature-pressure only works higher up in the atmosphere. So what we're trying to get at, I think, in that question is more elevation,
Okay.
right? So which one's higher elevated than which other one, right? So the higher up you go in the atmosphere, the lower the pressure becomes, right? So that's sort of more, I think, what we were trying to attack. Not so much the temperature-pressure relationship.
Okay, so we're just looking at like sort of the height of the ground.
Exactly.
Okay.
Yeah. Yeah? Cool. Yeah, so, okay, so how do you normally attack, like, numbers like that on there's, like, two things you could do, right?
Yeah, because it's like we did that. We divide by plus 900 or 1,000.
Okay. Exactly, 100, whichever one makes more sense to you.
quick, I hope, because I think I have the idea.
Okay.
Here, like, you have to identify which way the wind is moving, right?
100%.
Which I think is counterclockwise because the little sticks are pointed that way.
Okay, so, I mean, what do you mean by counterclockwise? Like, down there?
Like
the whole
this-
wind is going counterclockwise?
Like, this is a low pressure system, so the winds are moving
Okay.
counterclockwise.
Okay.
Because the wind direction moves with the little stick, right?
Yes, the wind direction is a little
Awesome.
stick.
Okay,
The
good.
stick is the wind direction, just FYI.
Great.
Okay.
And so if you have a system like this, then the cold air is coming down here, so this would be the colder air, this would be the warmer
100%.
air.
100%.
Okay, I was just
Yeah?
a little bit confused about how that was
Literally
working,
just
but
look at the direction of the winds they're going and just think, like, what air mass they're bringing with it, right?
Yeah.
If they're coming from the south and going north, we're getting
Okay.
warm air. If they're coming from the north,
That's not too bad.
Yeah, right?
Sometimes this seems harder than I think. And also, like, mean sea level pressure, that's just the sea level pressure, so is that the mean? I mean, it's
Yeah,
the
yeah.
number
Okay,
we're
but you
getting.
have to sort of, it's not that, like, it's not 103,
Oh, okay.
right? So when we give station data, I don't know, I think just for purposes of it's, we can't write that much stuff on it, we give, like, the last 3 digits, right? And then you have to decide whether to put a 10 in front or a 9 in front. Does that,
Right.
yeah? So we have, like, this is 103.
Oh, yeah. Yeah.
You just put a point here, right? So it's something blah 10.3, and then you need to decide if it's 9 or if it's 10.
Because you're trying to get closer to 1,000.
Yeah. So this would be like a hurricane center. So we don't think we're in a hurricane. So it's 10. Yeah?
Okay, yeah, that's awesome.
That makes
Thank
sense?
you so much. Yeah.
Perfect.